Hi, my name is Erika Pelaez. I'm from a city called Puebla, which is really close to Mexico City. So about 7 months ago, I moved to Seattle with my husband and my little dog. And what I found out was that we have really awesome neighbors. They are the orca whales, or as you might know them as killer whales. So it turns out there are resident whales in the North Pacific area, specifically in the Puget Sound area. And we have 3 different pods of whales, the J, K, and the L. Our resident orcas are very, very chatty. They're very active, and they use a lot of vocalizations. They actually have 3 different noises that they usually do. This is like, the first one is a spectrogram of a call, the second one is a whistle, and the third one is a click. If you are not experienced with this type of representation of sounds, you can basically assume that we have like a temporal aspect to this, and also a summary of the frequencies in the y-axis. So you can see how loud or how potent this sound was based on the color on each of the pixels that you see. Now, the problem is our orcas are being endangered. The population of the pods that we have in Seattle is decreasing. The reason might be the decline of the salmon that they consume, which is the Chinook salmon, but we still need a way to understand more their behavior and why they are disappearing. So that's why there is a team that's called Orcasound, which I recently learned from them from a hackathon that I was participating in. What they do is just basically listen for whales. They have a web app here, and we can even try to listen to what it is doing now. I don't know, should I connect the sound or not? Well, we can try and see what it does or not. It doesn't? Okay. Well, what Orcasound basically does is they have hydrophones, which is a fancy name for underwater microphones. So they have these hydrophones connected to a Raspberry Pi, which is recording every 5 seconds of sound, and then is sending that to an AWS. And then we store the sound, and then at the same time we send that sound to the app so that us, the listeners, can listen to like real-time sounds from the ocean. So we have what is commonly called like passive acoustic monitoring, meaning we have a lot of data. We have a lot of recordings from sounds and from whales and from ships and from whatever is going on under the water. But what we lack of it is labels. I'm glad we have a lot of talks before mine, so we can now appreciate the problem of having unlabeled data. So let's see what we have right now. We have, basically we have an unsupervised problem, unsupervised data set, because we have a lot of data that is unlabeled. So we could try to match, like look for patterns within our data and try to find groups within them. But the actual question, the actual thing that we want to do is we want to be able to tell whether the sound incoming is an orca or not. So what we actually need is labels from the data. But as it was previously pointed out, like labeling data is very time-consuming. Like nobody wants to really sit and do that. And why not try to combine both? We can do something called like a semi-supervised approach that you can come up with. So I could try to use a simple model to try to guess more labels and then gather more information to build a more complex one that gives us the answers that we really want. So the overall strategy that I came up with is, okay, I need to get labeled data. And I am assuming that as I'm a human, I can hear to any orca sound, I can recognize it, and I can extrapolate that information to any other sound that is similar to the orcas. Then I need to create a simple, classic machine learning classifier because it's less costly than doing like a neural network or something like that. And then try to infer other labels. And then I need to be able to test the performance of the classifier that I built with the actual data that I'm going to be using. In this case, the actual data that I'm storing in the Amazon service. And then I'm going to repeat the cycle until I come up with a model that I'm really happy with, and then it starts like giving answers that we are looking for. So the first challenge was to, okay, I need to find data, label data, and I don't know, maybe because we are data scientists or engineers or whatever you want to call it, like I think we prefer like coming up with a script that will scrape the web for labels instead of just like sitting there an hour. Like it will take you the exact same amount of time, but you're rather doing like in a hacky way, right? So that's what I did. I did as a web scraper that gave me label data from Orcas, like dating back from the 1960s. And then I said, okay, I'm going to set up the class for the Orcas, and the non-Orca class will be other marine mammals. Now, the second challenge that I found was, okay, now I have my audio signals. I need to do something to it. I need to pre-process them, and then do some feature extraction to fit my classical machine learning model. Like we saw earlier, classical machine learning models are very sensitive to the features, so you have to be more careful about the feature engineering part in this type of models. So what I did is like I found this amazing library that I use because it really takes care of everything you need to take care of. Like sample rates is like basically how many data points you have per second of audio sound. So everything has to be uniform, right? So it does that work for you. And then I need to do some feature selection, and I chose to do some male filtering and then the spectrogram to get the features. And I use LibRosa for that purpose. And then after, okay, so this is my features, basically. I have the male spectrogram. So what I basically did is, okay, I need like a vector of inputs. I cannot like give an input as a matrix, at least for the algorithm that I was using. And then what I did was, okay, I need to focus on the frequencies. So I basically have 128 like different bins for frequencies, and then I do the sum across of all of those. And then I normalize the vector so that everything in the vector, like the 128 vector, is summing up to 1. So I kind of have like a metric of the distribution of the frequencies, if you want to call it that. I mean, it's nothing that is already established, but that's something that I came up with. And then, finally, I built, with that handful of features, I built a random forest classifier. So like I already told you, I have my Orca versus other marine mammals class. And then doing a tenfold cross-validation and reporting precision and recall and then F1 score, everything would look perfectly. I was super excited. My accuracy was 99%. I was like, wow, this is really, really good. So now that I have this super great model that I built, I have to test it with the wild data. But it didn't work. Okay, so we can actually gather and see what, I mean, okay, so the data that I trained my model with is basically the green and orange dots. The green dots are the non-Orca class, other marine mammals, and the orange dots are the Orcas. So when I had 1 day of recordings, which are the blue dots, and I passed it to my model, it basically said, everything is an Orca. I was like, that's not possible. How can that be? That's impossible. And then I used that emoji, and I was really, really like discouraged. So okay, now round 2. Let's try to see. Okay, I saw that in this representation of the 2D representation of my data, I have some kind of structures. If you can see, there's like a group here, and there are some like kind of little clusters. So I thought maybe I could learn something from my data instead of the data that I scraped from the web. So I tried to use the hydrophone data itself, and I set aside a subset of the data, and I had to listen for about 35 minutes of data and like manually saying, okay, this is an orca, this is not an orca, this is an orca, etc. And instead of using a binary classification, I approached that as a three-class classification, because while I was listening to the sounds, I realized there's like 3 distinctive noises that I have. Well, there's actually 4, but I decided to go with 3. The 3 noises are the orca sounds. There's some level of background noise that everything has it. Like even when there's 2 a.m. in the morning, you have that sound. And then something that I assume are the ships, because they're really, really loud and really annoying. I would be complaining if they were my neighbors. I did pretty much the same processing that I did to the previous data set. And again, I got an accuracy of 99%, and all of the scores were perfect. And this time, I was dubious. Like, is this going to work? Is this going to finally work, or what? It turns out it is better. We have the same color coding here. So this is the whole data, and the orca predictions are in orange. The ship predictions are in green. And the blue predictions are the background noise. So as you can see, this part, I'm pretty sure it is a background noise, because we saw that same structure in the previous representation, and in this one, it all seems to be close together. By the way, this is a T-SNE representation of that, meaning I try to preserve the local structures in the higher dimensions and like portray that and embed that into a 2-dimensional space. So everything that you see here is like closely, like everything that's close here is close in the higher dimensional space. So apparently it does better. But I want my model not to just do better in this data, right? So I want, like I told you, I'm a human, and if I heard the recordings that I scraped from the web and I heard the data from the hydrophones, I should be able to know this is an orca, whether they're coming from different populations or not. So what I did was, okay, I'm going to test this model with the data that I scraped from the web. And I learned like some interesting things here. So I had to dip a little bit. I had to dive a little bit deeper to understand here. So this is the training examples. Like I chose random images of the training examples in the first row. So I have the first one is the orca class that I said, okay, this is an orca class. The second one is the background noise. And the third one is the ships. So you can see they're very, very distinctive, and they have different patterns. So now it's time to pass the other data set that I wave scraped. So this is the Orcasound. And this is orca, and it's also predicted as an orca. And you can see there are similarities between these two. Actually, between all of these columns, you can see similarities. Even though it's predicted as a not orca, you can see this is very, very much like this image. Like, if I was just looking at them, I would be like, yeah, maybe it does make sense. So I'm happy because these tell me that my predictor is just not doing something randomly. It's actually learning some type of pattern within the data. When I look closely at what it's actually doing, this is actually comparing the 2 models. This is the first model that I made with the web scrape, and you can see each of the row here is one of each of the 128 attributes. So I'm saying, okay, the model is paying more attention to the higher frequencies here and the lower frequencies here in the first one. So what I'm guessing the first model was doing is basically just saying, okay, I'm gonna specialize on the higher frequencies, and you can see these examples have higher frequencies, and this is what I'm gonna say as this is not an orca, and the rest is gonna be an orca. So I got some, okay, this is why my first model didn't work. And the second example is a bit more diversified. So the attention is not on the higher frequencies, but actually on the middle region, on the middle part, which is actually where we get the orca calls and the orca sounds here. So yeah, if you compare the 2 models, you can see why one failed miserably and the other did actually better. but like a week ago, I realized Google already did it. And I was like, okay, great. But I was like, okay, it did it with humpback whales, and they actually approached this not as a sound problem. They framed this as a computer vision problem. So what they did was turn the image classification into something with a CNN, with a convolutional neural network that we already saw. The greatest contribution, I think, to that work that Google did was doing one technique to normalize the sounds with piecing, or what they called. And that's something that they found improved their metrics, their performance metrics by 24%. So that's like going from 65% of accuracy to 90%, which is really, really awesome. So I'm going to try that one. And they also use a non-supervised approach, which to me sounded like a semi-supervised, because they use actual like label data, and then they use to try to find similar images to those. Like they use their algorithm and try to find similar noises and in this case are songs, like humpback whale songs. So the further task that I'm going to do is like validate the label data. This is the most difficult one, even though it's the easiest, because you have to actually see through all of the data and say, okay, my model actually predicted what is right or not. So that's the one that I'm delaying. But I'm actually working on the second two tasks. Like, I already have a CNN trained for that. I'm waiting for testing the performance of that. We can also implement something that's called active learning, which is basically you have something like I did, like a predictor, and then the labels that you have the most certainty about them, you leave it as it is, and the ones that lie in between the scale, you give it to a user or to like a critic that says, okay, this is like just to label them. And then you retrain the model with the new labels and the previous labels, and then you do the same over and over until you have a good model. So we have already the infrastructure for doing the active learning part, and I'm already working for the training part. I'm also going to implement this because it was a great improvement in their networks. And some cool projects that I want to try is like use GANs to generate Orca noises. And if I do this, I'm going to name it Dory, because I will be able to speak cetacean. And then also, other thing that I'm already working on is like, I want to apply this model that I built to alert users to when they need to hear. Like, it's like, hey, guys, an orca is doing the sound, and then they can go to the web app and actually listen to orcas, instead of just listen to noise. And if you have any idea or contribution to the project, or we are open, this is an open source project, and we are already welcoming everyone. So, thank you.